Hello, back again with another installment of video lessons here. This video lesson is going to be on classification of matter. Okay, I'm going to show you the ways that we break down matter and talk about the various components of it, and hopefully you'll be able to identify the differences in all the various types of matter we have. Okay, so this diagram here basically is showing us how matter is broken down. So matter, hopefully you remember, is anything that takes up space, which means that it has volume, and that it also has mass. So that's pretty much everything we can think of that we can hold in our hands or we can measure the mass and the volume of. So air and rocks and water, all that kind of stuff is going to be considered matter. Well, matter is classified in two big broad categories. Matter that's mixed together, and that's usually how we find it. Think about the Earth. The Earth is mixed together with rocks and water and gases and everything. So the Earth is one big heterogeneous mixture. Okay, the universe is one big giant heterogeneous mixture with planets and star systems and stuff like that in it. So we're going to break those mixtures up. Now what we can do is we can take, for example, going back to the Earth, we can separate the Earth, the solid Earth, from the liquid Earth. That would be using a physical change. So what we can do is we can get rid of all the water and put it together, and we would have what's called a homogeneous mixture. Now, just make sure everybody knows the terms here. Heterogeneous means different. Okay, so heterogeneous means that you can see the distinct differences. And if you look at the Earth, you can see the blue water and the brown earth and the green grass and all that stuff, and the blue sky. So you can see the differences in the Earth mixture, which we break it down, we can then separate it into what's called a homogeneous mixture, which means it's the same throughout. Okay, so it's the same throughout. So it looks as if it were just one big thing. Now the water on the Earth is actually a mixture, because we know that the water in the Earth is actually salt water. And there's things dissolved in the water, but we just can't see those differences. Okay, so salt water would be an example of a homogeneous mixture. Okay, and I'll show you examples of this stuff in just a second on another slide. So that would be a homogeneous mixture, heterogeneous. We can separate them using the physical properties. We'll talk more about the separation techniques in another slide as well. So if I take the salt water, okay, what I can do is I can break the salt water up into its pure substances, because we know that salt water is composed of two things. Salt water is composed of, hopefully you know, salt, which we would say is sodium chloride, table salt, and obviously water, H2O. So what we're doing is we're breaking up that salt into its pure substances, into its compounds, which would be the water and the salt, two clearly distinctly different chemical compounds. Okay, so that would be our pure substance. So taking the Earth, which is heterogeneous mixture, separating out the air, the gases, separating out the Earth, the solid Earth, the dirt and the grass and the rocks and all that, and getting it down to its salt water, which is now its homogeneous mixture, and we break that down into salt and the water, and we have our compounds. Now, sometimes we can have pure substances found in the Earth. So sometimes if you're looking around, if we were to go back to the solid Earth part, we could do is we can look at the soil, and we have different various components. We don't really find too many elements in nature by themselves. Usually they're held together in compounds. So we don't find aluminum, we don't find iron, we usually find iron oxides, iron ores, find aluminum oxides. We find most of those compounds, you know, all the elements chemically combined together already. We do find some though. Things like gold and silver tend to be found in the Earth as gold and silver. You can actually find a gold nugget or a silver nugget in a mine. You really don't find sodium metal or lithium metal. Not that you usually don't. You'll never find it. You're just not going to. Those are always chemically combined together. So we have our chemical change. So if I take the sodium chloride, I can break it down into its elements, into sodium and into chlorine, and that would be another type of pure substance: sodium, chlorine, hydrogen, and oxygen. And I'll talk to you a little bit later about why I'm putting 2's down here for hydrogen and oxygen. But for now, we have these elemental states that our substances can come into. Okay, so that's your differences between how matter is broken up. So let's just take a look at mixtures. All right, now as I told you, there's two classes of mixtures: heterogeneous. So those heterogeneous mixtures are ones that are going to be different, that you can see the distinct differences in them. Okay, and then you've got the homogeneous. That's an E, by the way. Okay, so that would mean that they are the same. Okay, all right. So salad is an example of a heterogeneous mixture because look, it's pretty simple. I can see the tomatoes, I can see the olives, I can see the onions and the cheese. So in a heterogeneous mixture, I can clearly see the distinct differences within our substance. Cookie is another example of a heterogeneous mixture. We can see the chocolate chips, we can see the cookie dough itself, okay? So we end up with the heterogeneous mixtures. You can see clear differences. Over here, in my example with the coffee is going to be considered a homogeneous mixture because it's the same throughout. You can't see the water, you can't see the coffee grounds that have been dissolved into the water, you can't see the sugar that's been dissolved into it. You couldn't see the cream if you dissolved it into it, so it would look the same and uniform all throughout. There's no complete distinct differences between the makeup of the coffee. Okay, these are considered solutions. So when we have a homogeneous mixture that's the same throughout, another name for them is solution. And in chemistry, they tend to look like this. But coffee is considered a solution too. So these would be our solutions. They're the same throughout. There's something dissolved in the water that's making it turn yellow, something making it turn red, turn blue. And it's uniform throughout, so therefore it is considered a homogeneous mixture. Okay, so that's your differences between homogeneous mixtures. As I said before, what we could do is we could extract whatever it is that's making that color. Water would be obviously the liquid form of it, and something else is inside of there causing the solution to turn red. So it's probably some sort of iron oxide of some kind. Okay, or maybe like an iron nitrate. Okay, we'll talk more about these compounds and formulas in the next chapter. So as you can see, I'm starting to write chemical formulas and symbols and stuff. So iron oxide, that's why you want to know those chemical symbols. If you haven't memorized them, you really want to start memorizing them because I don't write iron oxide out. I'm not going to write iron nitrate out. I'm going to be writing formulas, and I need you to know what I'm talking about. Okay, so if I'm going to break down my solution into the components that make it up, we need to talk a little bit about the differences between compounds and elements. Okay, so if these are my compounds, this is my compound of water, okay, made up of 2 hydrogen atoms and 1 oxygen atom. What I could do is a chemical reaction could take place where I take that water, okay, and I can actually perform an electrolysis reaction on it, and I can produce hydrogen gas and oxygen gas. Now, I'm not expecting you to be able to balance equations or write equations yet. We're going to get to that. But I'm just showing you that whenever we have a compound being broken down into its elements, it's going to have to go through a chemical change. It has to, because I am now changing the substance chemically. This is water, and water is a compound composed of hydrogen and oxygen. We can drink it. Okay, we swim in it. We can't breathe it. It's not going to blow up or burn. But over here, hydrogen is highly combustible. Oxygen is a gas. We breathe it. We need it to survive. We can't breathe the water, and we can't burn the water. So we've got clearly different properties between our substances. Same thing with carbon dioxide. If I break down carbon dioxide gas into the elements that make it up, we get carbon, which is a solid. And we would also get oxygen gas again. Okay, this carbon dioxide is what plants use to survive. They photosynthesize the carbon dioxide and create energy. Well, carbon they can't use, and they can't use oxygen. So to a plant, these two are no good. It has to be in this form here. So, as I said before, carbon dioxide and water are compounds, while these are your various elements. Now again, I'm writing 2's down here. I'll explain that a little bit later. If you don't have 2's, it's not a big deal. I'm more concerned that you know hydrogen is H, oxygen is O, and there's a reason why I'm doing that we'll get to later. So here's our compound. Elements that make it up are nitrogen, hydrogen, hydrogen, hydrogen. Okay. Now one thing students get mixed up with is the difference between compounds and mixtures, because it looks like this would be considered a mixture of hydrogen and oxygen. You could kind of maybe say that, but the problem is the difference between a mixture and a compound is this. If I have the water molecule, if I draw it out, I have 2 hydrogens on this water molecule and an oxygen. And they're bound together with chemical bonds that hold those 2 or these 3 atoms together as a group. Now, that molecule will stay intact as long as these bonds holding the hydrogen and the oxygen together do not break. So if I have a solution, a mixture of water, let's say that this is water, and I put inside of that water something like sodium chloride, going back to the example of salt water, and I put sodium and chloride in here. Okay, so what that means is that these two are not chemically bonded together. What's happening is that inside that structure, in between the water molecules, those sodiums and the chlorines are nested between them. So they're surrounded by, this is actually what's called a positive charge, we'll get to a little later, and chlorine is a negative charge. Okay, but what's happening here is that that water molecule is actually going to be in between those two molecules. This is still chemically bonded together. Okay, even though these ions kind of separated, it's still sodium and chlorine. Those haven't changed at all. They're still in there together. So the difference between a compound is that it is chemically bonded together. So yes, I am mixing oxygen and hydrogen together, but I am chemically bonding them together. Here I'm mixing sodium chloride and water together, but I'm not chemically combining them together. They're just stuck to each other because of that attraction force, because of the charges on them. And we'll get into solutions later. We'll talk more in depth about why they form and how they form. But for right now, realize that the difference between a mixture is that it's no chemical bonds are formed. It's just mixed together. They're just sitting next to each other. Here they're chemically bonded together in a compound. And that's a big difference between mixtures and compounds. Okay?